This is the first fusion power plant anyone has designed down to hard numbers. Magnets more than twice as strong as a hospital MRI. 12 million amps of current circulating in a plasma hotter than the core of the sun. And at least 400 megawatts of electricity flowing out to the grid. The machine does not exist yet, but in June, the physics behind it passed peer review. 5 papers that read less like a promise and more like a checklist.
The plant is called SPARC, and it has an address, Chesterfield County, Virginia, on the site of a retired coal plant, where the company behind it says it will feed the grid in the early 2030s. Inside, hydrogen fuel gets squeezed by magnetic fields inside a donut-shaped chamber until the nuclei fuse and release energy, about 1.1 gigawatts of fusion heat if the design works as calculated. And that "if" is exactly what the new papers are about. In early June, 58 scientists from Commonwealth Fusion Systems, MIT, and universities across 3 continents published the physics case for SPARC in the Journal of Plasma Physics. Not a press release, 5 peer-reviewed papers that ask in public the 3 questions any fusion power plant has to answer. Can it keep its fuel hot enough? Can it take out the exhaust heat without melting itself? And can it survive its own failures?
Fusion companies have made big claims for decades. What makes this one worth taking seriously is a magnet. In 2021, this team ran a new kind of superconducting magnet up to 20 Tesla, roughly 400,000 times the strength of Earth's magnetic field, using high-temperature superconducting tape that had never been built into a fusion-scale coil before. Stronger magnets change the geometry of the whole problem. Double the magnetic field, and the same plasma performance fits in a machine dramatically smaller and cheaper. That is why SPARC can promise power plant output from a vessel whose mean radius is about 4.5 meters, a machine that fits in an industrial hull designed by a private company instead of a 35-nation megaproject. So here is question 1 from the checklist. Can SPARC keep its fuel hot? The plasma sits inside a magnetic cage, with field lines twisted into a helix so particles stay confined as they race around the ring. But plasma is turbulent. Heat constantly leaks across the field lines, and if it leaks faster than fusion replaces it, the reaction fades. Predicting that leak rate is the hardest calculation in the field. The performance paper attacks it with a hierarchy of models, and it does something companies rarely do. It prints the disagreement. The mid-fidelity models predict SPARC makes roughly 900 to 1,300 megawatts of fusion power, comfortably above target. The most expensive simulation, a full nonlinear turbulence calculation, comes in lower under nominal assumptions, 677 megawatts. The gap traces back to assumptions about how sharply fuel density peaks in the core. That gap is not a scandal. It is the actual state of the art, published where anyone can check it. Question 2 is brutal in a way that surprises people. The exhaust. SPARC's core will run above 100 million degrees Celsius, and the nearest solid surface sits about 1 meter away. All of the heat that leaks out of the plasma gets funneled along field lines into one narrow gutter at the bottom of the machine, called the diverter. Focused there, the power flowing through that channel would rival conditions at the surface of the sun. No solid material takes that for years on end. The exhaust paper's answer is to never let that focused beam actually land. SPARC would puff impurity gas into the exhaust region, so the incoming heat gets absorbed and re-radiated as a diffuse glow spread over the chamber wall, a state physicists call detachment. The papers argue detachment can work at power plant scale. Just as important, they map which parts of that argument still rest on extrapolation. Small plasma edge eruptions, fine. The large ones, called ELMs, have to be avoided entirely. Question 3 is the one that keeps tokamak designers up at night.
Those 12 million amps of plasma current store an enormous amount of energy, and the surrounding magnetic system stores more. If control is ever lost, a disruption can dump energy into the machine in milliseconds. The disruption paper sets a target that sounds almost mundane, and that is the point. Disruptions should be engineered towards zero, but the plant is designed to handle about 1 mitigated disruption per day, restart within tens of seconds, and treat an unmitigated hit as rare. A companion paper on plasma stability maps the safe operating territory that control systems must never leave.
Every one of these papers, on every open question, points at the same building in Devens, Massachusetts. SPARC, the smaller test machine this team is assembling right now, runs the same magnetic field strength and the same physics regime as ARC. Its first magnets went onto the assembly stand this year, and first plasma is targeted for the next year or so. SPARC's job is to measure everything the models currently assume: how the fuel peaks, how detachment behaves, how often the plasma misbehaves. And in a quiet but unusual move, ARC's design is deliberately unfinished. The team calls it locking the design late. Key parameters stay adjustable until SPARC data arrives, so measurements, not projections, set the final machine. If SPARC shows the turbulence models were too optimistic, ARC gets retuned before the expensive parts are ordered.
There are real limits to what these 5 papers claim. They are plasma physics, not a finished power plant. Tritium fuel breeding, reactor materials that survive years of neutron bombardment, the economics, the licensing, all of that lives outside this collection, and some of it is as hard as the plasma. The 400 megawatt figure is the company's design target, not a measurement, and the early 2030s date is a goal, with a fusion industry track record that says treat every date gently. But something did change in June. For 70 years, fusion power plants lived in conference slides, where nothing can be wrong because nothing is specific. ARC is now specific: a named site, a fixed field strength, a printed power number, and a published list of ways it could fail, open for any physicist on Earth to attack. Within a few years, SPARC will start replacing those assumptions with measurements, one by one. Either the checklist holds, or we will know exactly which line broke. That is what it looks like when fusion stops asking for faith.